Good morning. We're here today to talk about formation sensitivity and analysis in the Upper Mannville. My name is Graham Spray. I'm the manager of geosciences for Agate Labs. When we're talking about the Upper Mannville, we're primarily talking today about the glauconitic sandstone and the blue sky. We're going to go through a bit of a regional setting overview, petrologic overview, and we'll talk about formation sensitivity in terms of what's actually of concern in Upper Mannville sands, how are we going to investigate and analyze these, the levels of concern, and the methods we might use. The regional setting is the early Albion. We're at about 105 million years ago in southeast Alberta, and we're looking at the western interior seaway as it transgresses southward as the Moose Bar Clearwater Sea. The prograding deltas are pushing westward into this seaway from the Cratonic continent, and I've put a little red star at approximately the location we're looking at. We zoom in on there, we can see these prograding deltas, and we're prograding in westward, and within these deltas we're going to see occasional fluvial channels as well. This is an overview of the isopack for the Upper Mannville sands, and the circled area is in the southern part of Alberta. Right now we're focusing in on part of the southern foothills, and what we're looking at is the stratigraphic sequences present in this area. And if we zoom in on the Upper Mannville, we can see we've got undifferentiated Upper Mannville and glauconitic sandstone underneath. However, it's not always underneath. In some areas, we classify channels within the Upper Mannville as part of our glauconitic sandstone. To the north of the area we're most focused on at the moment, we see these glauconitic sandstone reservoirs developing as prograding deltas, again prograding westward. And if we move a little bit further south, we see more of this fluvial channel influence, and within the undifferentiated upper part of the Mannville, we are looking at these channels that are scattered throughout the whole area, and we're counting those as part of the glauconitic sandstone. For a petrologic overview, we are looking at an immature fine sand. It's generally very poorly cemented and friable. It has fairly weak poro-perm relationship. We can actually see quite high porosity with low perm, and even vice versa. Depending on the types and quantity of secondary mineralization that has occurred. There's a huge continental influx. We're talking about quartz and feldspars, a lot of rock fragments and chert, making this quite immature, and clays and carbonaceous material as well. Most of the deposition is considered marine, especially because we have a lot of glauconite present. Glauconite development does require a marine setting. The diagenesis involves compaction, clay recrystallization, and development of orthogenic minerals. We have a lot of grain dissolution evident and cementing in terms of iron especially. So what we're going to talk about is some of the formation sensitivities that come up in these sands and how we might go about addressing them. In particular, we're interested in fluid sensitivity, so that's fluid compatibility, fines mobilization, iron liberation and precipitation, and Upper Mannville sediments which have similar properties. So for instance, the Clearwater sands. What we have in these sands is a lot of very complex clays with high cation exchange capacity, in particular smectite and mixed layer clays. In the image to the right here, we see a very well zoomed in scanning electron microscope image of pore system within this rock. And what we have is a very prominent zeolite crystal that has mineralized in the middle there, but it's sitting on a bed of petal-like corinthite, which is a mixed layer clay. And so we have a very high surface to volume ratio of these clays, and this gives us a situation that's ripe for the problem of swelling clay. So if we change the fluid chemistry surrounding these clays, we can induce physical swelling up to 10 times their volume. This means that we need to be very, very careful when we're considering the chemistry of drilling mud, enhanced oil recovery injection fluid, and so forth. Fines mobilization, this same slide still applies. That zeolite mineral there sitting on top of the corinthite is not particularly well adhered. And what we're going to end up with is the possibility, if we increase our flow rates too rapidly, of taking minerals like this, plucking them out of their current location, and dragging them through the reservoir, where they may build up in pore throats and plug things up. Another example here is kaolinite. This is a kaolinite booklets that are loosely adhered to the surface of a quartz grain. And again, if you start to increase your flow rate, in combination with chemical changes as well, which might actually precipitate them breaking off and starting to flow, we could well have serious implications for our drilling, enhanced oil recovery, and production flow rates. This is an example of grain dissolution. What we have here is a plagioclase that has had grain dissolution along the length of intersections within the cleavage of the plagioclase crystal, and that has left these shard-like projections sticking up into the pore space. These shards can actually dislodge themselves and start flowing, but also there's a lot of implications for the ions that have been released into the fluids surrounding all of the other minerals, and so we now have a lot of different fluids present that may react. Iron liberation is a potentially serious concern. A lot of these sands have ferroin carbonate as a cementing agent, and what we end up with is if we start to dissolve away these cements, the iron is liberated and becomes a kind of gel-like obstruction and is very, very difficult to get rid of. It can basically occur as iron oxides, iron oxyhydroxides, and these strange iron silicon oxygen kind of masses which are amorphous. These are very insoluble, so you can't really redissolve them, and they are low mobility as well. So when we want to figure out which ones are the most concerning the particular production or enhanced oil recovery or other process that we're looking to carry out underground, we need to investigate with a formation sensitivity analysis. This is considered a geologic study, and it can be done prior to more advanced investigations, such as physical testing of core plugs, to investigate the susceptibility of the formation to various damage mechanisms and determine which ones are most concerning for the process of interest. This can be done using core or drill cuttings. It's a project that's led by a petrologist, and it's kind of a qualitative risk assessment. We're not quantifying what flow rates are going to be problematic, what salinity is going to be required. What we're doing is saying which one of these potential damage mechanisms is the most concerning. But then does inform which way we are going to go when we start to try and test what kind of salinity, what kind of flow rates are going to be the critical rates. Formation sensitivity is usually done as part of a general reservoir quality study. So we would combine this with investigating the porosity system and the likelihood of perm damage based on some of these factors we've talked about. What we're going to look at is the rock texture, so that's the mineral deportment as well as overall mineralogy. We're going to look at core scale lithological setting if we can. If we have a core, we'd love to be able to have a look through the core and identify zones of interest of likely low risk and higher risk. We're going to interpret the sensitivity of the system to damaging processes, such as the clay swelling and the fines mobilization, iron gel generation, and phase transitions. This example here is an orthogenic smectite, grain rimming clay, mineralized right into a pore throat. So this is a really great example of some of the potentially damaging situations we see. Other applicable tools that we often apply are X-ray diffraction, petrography, scanning electron microscopy, QEMSCAN, XRF, including both wavelength dispersive XRF and handheld ED-XRF profiling of a core, core and cuttings examination, well log study, an interpretation of all the possible data that's available for this interval, for this core. So what I'm going to do is go through each of these techniques a little bit and just talk about what we intend to get out of them and how we use them in the context of sensitivity analysis. XRD gives us the clay mineralogy. That is, it gives us overall mineralogy, but its number one advantage is it can give us all the clays and differentiate them quite nicely. It's an industry standard tool for doing this, and we now do it very effectively using Rietveld refinement where possible. When we do have a lot of smectite and mixed layer clays present, we actually cannot use Rietveld refinement. The patterns cannot be refined using that mechanism, so we revert to a somewhat older technique called relative intensity ratio. A petrographic study involves making a very thin slice through a rock, mounting it on a glass slide. It's usually 30 microns thick, the rock, and we're going to be able to pass light through it and look at the crystallography, look at the structure, and look at the mineral deportment. Where are these grains relative to each other? Because, of course, the XRD is giving us the bulk overall mineralogy. It's unable to tell us how these minerals relate to each other, which ones are the main grains in the system, which ones are grain rimming, and that kind of thing. Also, we can investigate things like microporosity using UV fluorescence. We can look at depositional environment. We can look at rock history, diagenesis, and all that kind of stuff. For scanning electron microscopy, we're looking at the very fine microtexture. We're zooming in great detail into the rock and actually looking at what's going on inside the pore system itself, zooming in on those pore throats to actually measure their width and see which minerals are present. We can also carry out polished section SEM examination, where we take a similar thin section to the petrography, but we polish the surface very finely. And then we can look at that with a backscatter and see the density difference between minerals, and also look at things like organic matter. QEMSCAN is a similar technology to scanning electron microscopy, but it takes it a step further, adding the ability to map and model the mineral distribution across a region of a slide. Or, in the case of disaggregated or particulate samples, we can mount them in epoxy and actually zap them to see which grains are which all the way through. So it provides some of the similar results of a thin section and an XRD, but from one tool. It can also provide us the particle sizing, so you can take all the particles and produce a particle size distribution, or you can even do that by mineral phase. In this example, we're looking at the two different modes of operation of QEMSCAN. We have two of these epoxy pucks. They're 30 millimeters in diameter, and then below that, a polished thin section. From the pucks, we obtain little maps of each individual grain within a puck, and from the polished section, we get a map over a region that is selected within that section. We can also do this at various resolutions, and we can zoom in on features of interest, for instance, this interesting replacement texture, to see what's going on in more detail. This is an example of the QEMSCAN particle size output arranged by phase. What's interesting here is you can notice at the very bottom of that chart, porosity is counted as a phase. So when we are mapping, especially on a map on a section, which we call a field scan, we can actually map the porosity as a type of mineral, if we like. We classify it as a type of mineral. That lets us treat it as one when we're doing our statistical analysis. In this example, we're looking at a map of a thin section in a dolostone with a secondary dissolution porosity. Geologists will recognize that we have shell fragments that have dissolved out, and the dark blue is the porosity, and you can see that there are still even shell fragment shapes present within those. Well, what we can actually do is tell the system, show me all of the porosity spaces. We could do this with any mineral, but as an example, let's use porosity. And what it'll do is it'll categorize them by size and also give us a size distribution for each of those, throughout the porosity size ranges. In this example, we can clearly see there's a bimodal distribution of porosity size, and the reason, of course, is that the secondary dissolution is much, much coarser than the primary porosity. XRF Core Profiling is something that we are seeing more and more lately as a type of chemostratigraphy analysis. What we're doing is we're taking a handheld XRF gun. It's very interesting. It looks like a futuristic ray gun. We're putting that onto the core surface, and at 5 or 10 centimeter intervals, we're analyzing a point to obtain the elements that are present at that point. The type of gun that we use can carry out all elements from sodium and up. It is unable to get carbon at this time, but we can actually model some of the other elements based on what we're seeing if we have good data from other sources. So this type of data, when you're doing profiling, each individual point is considered semi-quantitative because we're trying to interpret mineralogy from elemental chemistry, which is a non-trivial process. However, what we do is throughout a core, we would tend to calibrate the XRF profile using control points where we have wavelength dispersive XRF for a much more accurate analysis of the elements, and XRD for a more accurate analysis of the minerals. This allows us to have confidence in our XRF profile that we then generate. When we have all of our data together, we're going to put together a report that goes to our special core analysis lab as well, and then they can have a look at that and see what we as geologists believe are the most threatening or the most sensitive aspects of a formation. This geologic analysis is done also after a formation damage testing in the SCAL lab. So what we might do is take plugs in the special core lab, force fluids through them, or soak them with fluids of interest to see what's going to happen, then take those and analyze them again in the geology lab to actually see what happened. One of the things we've run into in this process is trying to preserve some of the very delicate mineralogy and features that form while we do the SCAL testing. These can be exceptionally delicate or even very soluble. So we have to be very careful with what fluids we use to prep our thin section slides or to take apart the plugs that were analyzed. In the example in the photo here, we actually have very clear fines migration. We have quite a coarse sandstone, but we've had migration of fines up against the screen that was present in the plug. And we could actually, throughout the whole thin section, see an increase in fines in the direction of throughput. So this was telling us that fines migration may well be a problem in this particular example. There are a few other fluid rock compatibility tests we can run in the lab. They're kind of quicker benchtop tests, again, fairly semi-quantitative or relative. And what we're looking at is things like clay swelling, precipitation of scales. And we tend to run them with groups of fluids because these are for comparative purposes. So the first one is hot rolling dispersion, also called the roller oven. What we do is we mount the sample into a heatable turning unit that allows us to mix a fluid with the sample material at the same time. And we would do this with, for instance, clean water and water with multiple different additives. So it could be a water with a sodium chloride or potassium chloride salt. It could also be a water with a proprietary chemical additive provided by a drilling fluids company. The purpose is to roll the sample at a certain rate and for a certain length of time, and then see how much of it was broken down to smaller sizes during this process. So if we see very little breakdown, it means that the fluids that it was mixed with were not precipitating a faster disaggregation of the sample. Whereas if we see a reduction in grain size, it means the fluids used were not particularly effective. In the example here, water was the least effective. Capillary suction time is somewhat similar, and what it's trying to do is show us how fast the sample will precipitate, or soak through a filter paper in different mixes of fluids. Similar idea, what we're looking at is how badly will the sample be inhibited from flowing through that filter based on the different fluids used and the interaction with the sample material itself. So the fluids that minimize the perm inhibition the most will absorb through the filter faster, so we get a lower capillary suction time. So that means that the faster times at the top there are the more effective fluids to have used. And lastly, the dynamic linear swell meter. This is simply a method for measuring physically how much a sample will swell when exposed to different fluids. In the example here, we're actually looking at, again, the same distribution of NaCl, KCl, and clean water, pure water. And we can actually see that although pure water had the worst response, it actually had a slower response as well than the other two. So the three methods together are exceptionally useful for giving us a quick benchtop comparison of some of the potential formation damage mechanisms that are present before we move on to these much more intensive and quantified SCAL tests. Thank you very much.